So here you see a classifier that takes a look at this image and assigns one of many labels, actually one of 101 labels, as you can see here. And one of the labels is a photo of guacamole, a type of food, and it assigns a really high probability to that, as opposed to like the second prediction, which is ceviche. So, you know, classifier, pretty good, okay. Take a look at this classifier. Out of 397 labels, it correctly identifies that this is a television studio. You can go on right here, and so this is a photo of an airplane. Whenever there's a green bar at the top, it means that the respective classifier has this correctly. Whenever there is an orange bar, it's an incorrect label, with the green bar being the correct label. So you can see here these classifiers perform sometimes pretty well on these examples and sometimes not. But what you can distinctly see is that these are all from different data sets, so different tasks. There is a satellite image, there is a car, and you're supposed to classify which car it is, not only that it is a car. So very diverse set of tasks. And the interesting thing is that this is all the same classifier. So this classifier it's not even fine-tuned. It is a zero-shot classifier that handles all of these different training data sets. Sorry, not training data sets. All of these different test data sets in one go. So that's already pretty cool, but what you may have noticed is that the labels aren't labels that you would usually see in a classifier. So, you know, these 101 labels here, they are, it says it here, guacamole. That's the label. Interestingly, the label the classifier assigns is not just the word, it's a photo of guacamole, a type of food. Okay, that's the label the classifier assigns, and the second highest label is a photo of ceviche, a type of food. It's not always a photo, though it is often a photo, but here you can see, for example, the label that the classifier assigns is a centered satellite photo of permanent cropland, where the correct label here is the annual cropland, which is down here. Again, the label is longer. So there's something interesting going on here. It's the same classifier, it's zero shot, so that means the classifier is not trained on these data sets. It's not trained to fulfill these tasks, yet still it seems to perform okay. And the labels are quite weird. So this is a new paper by OpenAI, which we're going to look at today. You can see it's a pretty long paper, but we'll cut it short, I promise. And it's called Learning Transferable Visual Modes from Natural Language Supervision. And the model colloquially, or even also in this paper, is referred to as CLIP. So this is the model has been released along with the DALL-E model, which, you know, can do the chair made of avocado and so on. The DALL-E model is a generative model that generates images. CLIP is more of a, I don't want to say discriminative model, but CLIP is a model that takes in images and text and connects them in a non-generative way. So we're going to see what that entails. It's by Alec Radford and Jung-Woo Kim and others, as I said, of OpenAI. So the idea here is to connect text and images, and this has been done in a number of ways previously. Even in this way, it has been done in one fashion or another. I find the introduction and discussion of related works in this paper to be very thorough and superb, so they do assign a lot of credit to people who have had the various ideas. So the goal here is that we want to get a model that can represent images and text really well. Okay, so how do we connect images and text? First of all, what if we have a data set of images and text? Okay, so they construct a new data set where there's an image, like something like this, a cat, and a little piece of text to it, like my my cute cat. Images and text like this you'll find on, for example, social media. You can scrape that, Pinterest, whatnot, Flickr. People write descriptions along with their pictures. So it's pretty easy to get these pairs of images and text from the internet without having to label them, right? So one motivation of doing this kind of work is if we train a image classifier model, we always need labeled examples into a very predefined set of classes. So in ImageNet, we have 1,000 classes, or 22,000 respectively. In MNIST, we have 10. However, if we could just somehow learn to connect images with the text that comes along, we wouldn't be bound by the classifier labels, and we could get very good representations. So the original idea, or one of the original idea, is we take the image and we predict the text from the image. Of course, DALL-E goes the other way. So DALL-E somehow goes the other way, taking the text and predicting the image. But the idea is, if we can take an image and from it predict the text, what we get out of it is not only a model that can label images, but what we hope to get out of it is this process right here may be very, very good representer. So if this is like the image goes into a neural network with a bunch of layers, and then out comes, the text, my cat, and so on, then somewhere in here, in the intermediate representation of the neural network, there must be a pretty good representation of what is in the image. So not only, the pixel values, but there must be actually some kind of representation of the concept of cat, because otherwise it could not predict the word cat at the end. Okay, so the idea is to get a really good representer, and then you could take that representation and fine-tune it to other tasks and so on. So that's one of the ideas we're going to work off here. And it turns out this is pretty useful. There have been papers before predicting the simply predicting the caption of images, but it doesn't work too well. So what this model here is going for, and we'll simply let's look at this graph right here. So they tried first to predict the text, and you can see that zero shot, and we're going to look at what exactly zero shot ImageNet accuracy means in this context. But you can see here that they had some success with using a transformer language model to predict the text in images and evaluating that on ImageNet. However, they seem to have more success by using just a bag of words prediction. So what that means is you're not trying to predict the exact words. You're simply trying to predict which words occur in the description. So you see the photo. If you predict cat and my and cute in any non-ordered, you're already correct. And that already gives a sort of a better efficiency. You can see the models here, they tend to go up, but it's questionable if that will ever reach the orange line. And with their new objective, with what this paper suggests, you can see right here, the contrastive method, you get a way bigger performance. So we'll look at what this zero shot accuracy means and why it might be that these simply predicting the text from an image might not be a good enough idea. So let's say we have a model that can do this. We have a model that can take an image and it can predict the text that appears in it, right? Most of the time, this model right here is also going to give you something like a probability, okay, like a likelihood. So if this is a transformer, you can ask, for its logits, and then you can compute the likelihood of a given label. So if you have such a model, what you can do is exactly what they allude to right here. If you have an image task, right, and you have a model that can predict the text of an image, you can take that image and you can run this sort of through your image and through your encoding pipeline, and then you can ask the model, instead of predicting a text, you can ask the model, how likely is the text dog? How likely is the text cat for this image? How likely is the text mouse? And then you get some sort of likelihood, right? So maybe it says dog is this likely, cat is this likely, mouse is this likely. And immediately you have built a classifier. So I hope you can see if I have a model that can predict how likely a piece of text goes with an image, I can, by simply asking my model for each of the classes that are possible in the task, I immediately get a classifier out of that. I mean, I'd have to normalize or something by that, but I immediately get a classifier. And now you can already see why we might want to phrase the things a bit. So I don't want to just put dog and cat right here, even though those are the labels in that task, right? If I had an ImageNet classifier, I would put all of the 1,000 possible classes and ask the model for each. How likely is that label to go with this image? And the model, can produce text. But the model can not only produce, the single word dog, the model can also tell me how likely is the phrase a photo of a dog. A photo of a dog. Or how likely is the phrase a photo of a cat, and so on, right? So, and you can see that this result here, the classifier result, it might change actually depending on how you phrase. So here you can use the exact same classes as you used above, but by rephrasing the prompt, so to say, you might get a better quality classifier or a worse quality classifier. So if you already know that your images are all photographs, you will get a better accuracy, because simply, the model, you might get a better accuracy by asking the model, hey, how likely is the phrase a photo of a dog going with this image versus the phrase a photo of a cat? That might give you a better signal, so less noise in whatever you get as an output, than simply going with the single word. Because again, this model is trained to predict this just from a data set scraped from the internet. So how often do people post something, I don't know, on Instagram of their cat and simply write cat with it, whereas maybe they write, here's a photo of my cat, right? So the phrase a photo of a cat is, or they do like hashtag photo, hashtag cat, or something like this. So that's why these classifiers at the bottom, they were constructed from the labels of the data set, but with a prompt that has been adapted by humans to work, find to work particularly well on that data set. So we're sort of back to prompt engineering here. So this is how we go from a model that can assess, predict text to a classifier, and that's a zero-shot classifier. We don't need to train this classifier on the actual task. We simply need to restrict its possible outputs to the classes at hand, right? This is it's a bit like a tiny bit like in Q learning, where in each step you ask your model, well, what if I do action 1? And then the model tells you, well, that's 5 good, probably. Your Q value is 5. And then you ask, well, what if I do action 2? And then the model says, well, that's 7 good, and so on. So it's sort of a similar concept, except Q learning, we usually train end to end with an actual classifier. But I said simply predicting text objective might not be good enough, right? So we're going to retain this property of being able to zero-shot classifier, but we're going to now switch out our task of how we get to such a model. So instead of predicting text, what does clip do? Clip does the following. So what we're going to do is we're going to take the image right here, and we're going to pass it through an image encoder, and that gives us an image representation, so a vector in some latent space. So this is image 1, and then image 2 right here would be image 2 here. Okay, so we have a mini batch of images, and that's important. Then we're going to take the text and feed it to the text encoder, also obtaining a representation for the text, right? A single vector for this entire text right here. And then, of course, if we go to the second sample in the mini batch, we get the second representation. And the batches, of course, in the training data set, we know that the first text goes with the first image, the second text goes with the second image, the third text goes with the third image, because that's how we scraped it from the internet. And then what we ask the model to do is simply to tell us, so previously we tried to predict from the image the text, right? We went through the image encoder, and from this representation here, we tried to predict the text. So we no longer do that. What we're trying to do is simply ask the model for this representation, which of these texts is most appropriate to that particular image. Okay, so this is why it's called a contrastive objective. We know, because this is training data, we of course know that image 1 goes with description 1, and image 2 goes with description 2. But we're going to train this in the way that, we feed in this image and we ask it to which of all of these texts right here, to which of all of these is this image the closest. And we're going to train it such that it is maximally close to the correct one and minimally and far away from all the others. So this is why it's contrastive. It contrasts what we know goes together, right, the diagonal elements in this matrix, with what we know doesn't go together. Actually, we don't know if a different description wouldn't fit the same image, but we can safely assume that a random piece of text, since we do the mini batches randomly, a random piece of text will probably not go with this particular image, at least not as well as the piece of text that we found it with on the internet. Okay, so what you get is effectively, for each input, you get a classification task in this direction. You can see right here, for image 3, there is one correct text that it goes with. And for each text, you get a classification task in this direction. By the way, this is simply an inner product right here, right? You're simply trying to maximize the inner product of things that go together and minimize the inner product of things that don't go together. So you multiply the two for the inner product, you interpret that as a logit, and then you do a softmax classification in this direction and the softmax classification in this direction. So this is a symmetric loss from the text and image perspective. And yeah, so it's a classification problem. It's like a classification problem viewed from two different angles. So you can immediately see that this relies on having large enough mini batches, right? So the larger your mini batch, as your mini batch size approximates the entire data set, your representations are going to be more and more detailed, right? So Pepper the Aussie pup being close together to this particular image means that in the ideal case, it is close to this image and far away from anything else in the data set. And as an approximation, far away from anything in this particular mini batch. And at inference time, you do very much what we did so far. So you take, if you want to build an image classifier, and the interesting thing is you can also build a text classifier, right? If you have multiple images to go with a text, then you can do that. It's entirely symmetric. But in this case, you take an image, you put it through the image encoder, you get a representation here, you get all the labels of your classification tasks, right? So this is the label is this right here. You engineer a prompt, and that you do as a human, right? This is heuristic. This you as a human think, aha, okay, I'm going to put whatever this is here. you encode all of these labels in their prompt context through the text encoder. You get the representations here, and you simply ask to which of these labels is it closest, right? So is the inner product the highest? And that's how you obtain the label. Zero training needed on the actual task, right? So the data set that you do this with can be an entirely different data set than you do this with. And this is extremely interesting. I've actually seen some posts on Twitter and Reddit where people use this to guide a style GAN to produce given pictures with given descriptions and so on. So the possibilities for this are pretty huge. Okay, so that's the model. The model, it encodes images, it encodes text, it does this contrastive objective, what goes together, what needs apart. And now you see why this might be a better representer than, for example, simply pre-training a model on an image classification task. Because if you pre-train a model on an image classification task, it is going to simply lump together all the dogs. You know, if this is your classification task, it's going to lump together all the dogs because there's no need to differentiate the individual dogs from each other, right? It's going to lump all of them together and forget that they are actually different, right? It's also going to forget everything that doesn't concern the immediate classification problem. Whereas this model here, this model is specific. As it gets better and better, it will pick up at more of the text, right? So in this case, maybe if the model is pretty weak, still it will focus on this pup, and that's about the same as saying, okay, it's a classifier of a dog. But then we can also Aussie pup, if it incorporates that, if it gets better, well, it can differentiate it from other dogs. And by the way, it's a pup, so it's a young dog. It can also eventually learn its actual name, right? And so on. So you can see that as the model gets stronger, it can pick up more and more nuances of the data set. So they test this, and they tested fairly extensively. And I don't think we'll have to go through all of it for me to convince you that this is a good idea. You're going to maybe see it approximately or immediately. So, yes. So they use different types of, yes, that's what I wanted to say. They use different types of encoders for the image encoder. So for the text encoder, this is a transformer. So transformer. It's not a particularly big transformer even. And they simply take the end of sentence token, the representation of that at the end, and that's their vector. If you don't know what a transformer is, I've done many videos on transformers. Find one of them, any of them. For the image encoder, they test out a bunch of different things. So they test out a bunch of variants of ResNet. I've done a video on that. And they also test out a bunch of variants of the visual transformer, the VIT, that has recently been popularized. I've also made a video on that. So that's why their model shows up in sort of different flavors and sort of different points here. They scale the amount of data, I believe, with the model. So they scale everything together, compute, data, and model size. And that's why you see different variants of the same model. They also do ensembling. So, you have to engineer these prompts, and what you can do is you can engineer better prompts, and that will gain performance. And you can also ensemble over prompts, and you can see right here that gets you both an efficiency gain if you want to stay at the same performance, and also, and also it gives you a performance improvement for the same compute with the same model, right? So here the corresponding dots are the same model. That's why they have the same compute. So that's just one of the fun things you can do. And again, I think prompt engineering will become quite a bit more relevant. So here you can see the comparison. Zero-shot clip is competitive with a fully supervised baseline, right? So the baseline here isn't too good. So it's a fully supervised linear classifier fitted on ResNet 50 features on 16 datasets, including ImageNet. So the ResNet 50 is a popular architecture. It's not nowhere near the absolute best we have, but it's a popular architecture. So this ResNet 50, what it has been trained on is has been trained on ImageNet. Right, so and that results in a neural network with a bunch of layers, including a classification layer at the end, right, into 1,000 classes. So what you do is you pre-train this on ImageNet, and then you simply take this part right here up until the last layer, and you take it. So that's this part right here, and you assume that this has a sort of a good representational power since it can do ImageNet, and then you simply train a new linear classifier on top that does the classification into whatever new task you want. So this is called, it's called linear probing. So linear probing, you can also do it in the middle, sort of, but in this case, they mean linear probing at the second to last layer, like before the classification layer. So you assume that whatever this is a good representation function, you keep it constant, and then you train a linear probe on top of it. This is compared to fine-tuning, where you would fine-tune the entire network on your new task. But they elect to do most of their experiments with linear probing, since it gives you a better indication of the representational power of the bases. So here they compare to ImageNet, right? So on 16 datasets, including ImageNet. So for ImageNet, you would expect the ResNet 50 to perform quite well, because its representational base has been trained on ImageNet, and training a linear classifier on top, it should simply give you back the performance that it had on ImageNet. And here you can see how zero-shot clip compares to linear probe on ResNet 50, right? Zero-shot clip compared to an actual trained thing, not the best, but a trained thing. And you can see that on many data sets, clip outperforms the ResNet 50. Zero shot, right? So no training required beyond the pre-training. That being said, the pre-training is huge. But it's similar to GPT-3, right? You train it once, huge training, but then you can do lots of things. ImageNet, interestingly, you see right here, it's actually improving ImageNet over ResNet 50. Crazy, right? Whereas, so ResNet 50 still better in various other tasks. So this is not to say that this is the new state of the art or anything, except in STL10, where it actually appears to be the new state of the art against all the previously, including all the supervised whatever. It's the new state of the art on this data set. And the reason is this STL10 data set, it has very few training examples per class only. So supervised is very difficult. Transfer learning is kind of difficult. As I understand it, it's not that similar to ImageNet. So that transfer learning is kind of different. So this really seems to be, this zero-shot clip objective seems to be good if you have images that are sort of natural, that happen a lot on the internet, but are not really like ImageNet. So there exist quite a number of those, and that you have few labeled examples of, if any, right? So that's a good application domain. However, on more specialized things, they say things like, tumor classification and so on, satellite images, this clip objective still does pretty poorly, probably because, that's not the type of images you find on the internet with a piece of text. Super interesting, MNIST, one of the easiest tasks in deep learning, it also quite underperforms in this thing. So that they do an analysis of these different data sets. So they compare to ResNet 50 and also to visual n-grams right here, and they discuss the importance of the different data sets. Oh, I found this to be very interesting. Most standard image classification data sets treat the information naming or describing classes, which enables natural language-based zero-shot transfer as an afterthought. The vast majority of datasets annotate images with just a numeric ID of the label and contain a file mapping these IDs back to their names in English. Some datasets, such as flowers and the GTSRB, that's a German transport street sign or dataset, I don't exactly know, don't appear to include this mapping at all in their released versions, preventing zero-shot transfer entirely. So what these authors had to do is they had to like look at the classes and then sort of label them themselves, because their model works on language, whereas this street sign data set probably just came with, this is sign type 1, this is sign type 2. They have a footnote here. Alec learned much more about flower species and German traffic signs over the course of this project than he originally anticipated. I love that. I love a bit of humor in the papers. And so I made this meme where the street sign is specifically tractors and trucks with an authorized loaded weight of more than 3.5 tons prohibited. I wonder actually how the model does on exactly this sign, but yeah, we'll find out. By the way, the clip model is available in, not the big one, but a small one is available, actually trained. So you can test it out, and maybe we'll do a video on it where we actually do something with it. So here you can see that if they compare their model to few-shot linear probes. So here they compare zero-shot clip with few-shot linear probe. So before we compare to linear probe, which means we just trained this linear classifier, but we did it on the whole data set. Okay, so here we simulate only having very few examples per class, which is where pre-training really comes in. And you can see that zero-shot clip outperforms a lot of models if you only give them very few labeled examples per class. In fact, it is comparative to a 16 label bit M. So this is one of the best models that is currently in the public and that is doing this transfer learning. So if you transfer learn with a linear probe, again, this is not fine tuning, with a linear probe on 16 samples per class, with this model, you are still only as good as the zero-shot, no training at all of the clip model. That is pretty interesting and pretty cool. The other noteworthy thing is that if you linearly probe the clip model, you way outperform the largest models there. And also, what is also interesting is that when you do labeled examples for clip, when you do linear probe on clip, the performance decreases first and only increases once you get to like 4 labeled examples per class. And that, you know, is pretty intuitive when you think about it. So what you're doing is, so in clip, the zero-shot classifier is actually a different one than the linear classifier. So the zero-shot classifier is in a way already trained, so it has already trained this sort of last layer, whereas if you do linear probing, you throw that away, you know, the whole part where you encode the text and you blah, 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 you throw that away and you simply do the old school. So the linear probe here, this is no more the is which text is close. This is simply, I take this, I throw away the last layer, I put in a new last layer, and I do my original classification task. And of course, this layer right here is initialized randomly, and it's going to require some training, and maybe, you know, one example per class isn't enough. It's just going to pick up on some spurious correlation in the feature, and that's why it's getting worse initially. but it recovers at 4 examples per class, and it severely outperforms the other models, so we'll forgive it. They do discover in various experiments here that it is very, very different from dataset to dataset how this model performs zero shot, how it performs versus linear probing. They find that very often in some datasets that are far away from sort of natural images, they perform worse. Again, in some data sets, they require lots of labels to match zero-shot performance. So it is really a study into sort of, I want to say it's a study into what kind of images appear on the internet. They do, interestingly, there is a trend in machine learning that if you give more data and compute, then your error goes down, even with the same type of models. And that seems to hold pretty well here, as you can see here, as they scale up. This is the same, this is a ResNet backbone. As you scale that up, zero-shot clip performance scales smoothly as a function of model compute. However, they do note that there is a whole bunch of variations. So the curve you're seeing is the average, but for the individual tasks in their task data sets, it varies wildly. So there's a lot of noise here. This could be because of how the data sets are selected. This could be because of how the prompts are engineered. There is still a lot unknown right here. They compare various other things like linear probe performance of clip models in comparison with state-of-the-art computer vision models, and they do outperform all of these other models, as you can see here. So there is 12 data sets in previous experiments, but the 12 are still sort of similar to ImageNet. But if you include more data sets, of course, that's sort of a selection bias or whatnot. But then this model severely outperforms all of the other models. So the red models here are, the red ones are the clip models compared to the other ones. So yeah, this seems to be a step forward in the sort of building classifiers for the average user, right? So I can now go ahead, take this model and build my own classifier pretty easily. They also make some interesting discoveries in terms of robustness, robustness to perturbations. So previously, all these models, they sort of pre-trained on ImageNet and so on, and people have discovered that as soon as you go away from ImageNet, the performance of these models decreases heavily. So if, for example, ImageNet v2 is just ImageNet, but they try to collect, I've made a video about that, by the way, they try to collect ImageNet as closely as possible to the original test set. They try to collect a new test set. And immediately, the performance of all the classifiers dropped in the light of this just slightly data-shifted data set. And if you sort of try to go away a little bit further, so you just have sketches of these objects, you sort of have this adversarial placement of objects. You can see right here, it's pretty mean, but still a human could do this, right? You see right here, these are just variations on the themes of ImageNet. They have the same classes. So a classifier trained on ImageNet should be able to also classify these images, right? So here they compare zero-shot clip to models that have been trained on ImageNet, and they find that zero-shot clip, even though it matches, so this zero-shot clip matches the performance of ImageNet. By the way, a huge achievement, right? This is a fully trained model on ImageNet. And this is not the state-of-the-art, but respectable top 1 performance on ImageNet. And zero-shot classifier matches that performance. This is crazy, okay? You can see as this classifier degrades as you go to harder and harder data sets that are all technically ImageNet images, like in the same classes. This classifier, it sometimes even, gets better, but it keeps up its performance, which you can see here the difference between it gets just larger and larger. So the clip is way more robust. And of course, this model right here is trained to predict these specific types of images. So it knows very well like how to keep them apart. The only thing it has to do as a classifier of ImageNet is keep apart the individual instances of exactly those classes in exactly this data set. So it forgets about everything else, right? And as a result, it has never seen a sketch. It like a banana is yellow. What are you talking about? So it heavily degrades, right? Whereas clip, it simply knows how to sort of connect images to text. So while clip realizes that, of course, both are described as banana, it somehow has to account for the fact that there are also lemons in here, right? It has to somehow represent that. It has to represent that this is a bunch of fruit and that this is here maybe a, high-grade picture like on a magazine, where this here might be more of a sort of random GoPro fallen into some bunch of bananas. It has to somehow represent all of this if it, performs well on its task, and thereby its representation will be nuanced enough such that it can transfer more easily. It picks up on different features than only distinguishing banana from, other classes in the ImageNet dataset. And that results, so here is the curve, in that if you had the ideally robust model, you'd have this right here, so the exact same performance on the natural distortions than on ImageNet in the original ImageNet. You can see that all of the standard ImageNet training examples, including all the robustness techniques that barely lift away from this curve, are massively outperformed by a zero-shot classifier that hasn't even been trained on ImageNet. And the fact that it hasn't been trained on ImageNet might be one of the things that it actually is very helpful. So they do some investigation into it, including that you can in fact adapt to ImageNet. So you can I think that's a linear probe. If you linear probe clip, you can improve the performance on ImageNet, where interestingly you can improve the performance on ImageNet by doing a linear probe on top of clip. So this is logistic regression clip, while only mildly degrading your performance on these other data sets. So there seems to be a value to just having the representation. So the representation itself seems to be more stable. Okay, so you can see as you adapt to ImageNet, this performance improves massively, but it only degrades a little bit across the other data sets. So that means, as I said, the representation itself is more nuanced, such that even if you train a linear classifier on pure classification, you'll still keep up the performance on the other tasks. You can also adapt to class shift, so by better prompt engineering for some of these subtasks, but I think that's a sort of a minor thing. All right. I don't want to go, too much. They also compare to humans, which is very interesting, and they discover that, samples that are hard for the clip model are also hard for the human model. They do some sort of duplicate detection from their training data set, because their training data set is 400 million images together with text, right? So it's conceivable that there's some duplicates, but they find even if there's generally not a problem. And they have like a 3 or 4 page broader impact section, as you can see right here, which, is, so if you read it, it reads sort of like Yeah, there are problems with these models. We are better than other models, but we're still not good enough, or things like this. Or they're like, yeah, this is, of course we're better. Like, they're better at everything. But then again, this is only preliminary. More study is needed, and so on. So they have some fairly interesting results. So what they do is, since there is such a focus on prompt engineering, right? It actually matters what you give to the model as possible labels. So this is no longer fixed labels. You can give any labels. So they have these data sets where for example, this fair face race, where you try to categorize faces into different ethnicities or races. These 7 things that are given here. They also include some non-human categories. Where is it? So they include categories such as animal, chimpanzee, gorilla, or orangutan, and they also include sort of crime categories like thief, suspicious person, criminal, and then they research how the model misbehaves, and these models, they do a fair bit of kind of misclassification right here, as you can see. They notice that the misclassification is especially there for younger people. So these are the ages of people, and here are the misclassification rates. You can see the misclassifications are mostly for younger people. Then they simply add a child category. And then the misclassification for young people all of a sudden drops, because the model now has the option to classify them as a child. So this, I think the result of the paper, and especially of the broader impact section, one of the results is that it matters a lot how you engineer the prompts, which is something we already knew, but of course this can be particularly crucial in some applications, in some concerning applications. That's kind of one of their points right here. You can see that the paper is huge, and it also has a huge appendix, and they do, as I said, a lot more experiments right here. But all in all, this is a very, very cool approach, I feel. And it's, as I said, a step towards making it easier for the everyday person to build their own classifier for, you can do quite niche tasks as long as they're sort of natural images. This will work fairly well. I think it's pretty cool. It gives a little bit of more freedom in how you work with these models. And I'm excited for people to come up with ideas of how to use this, how to connect this to other models, such as you can connect it, as we already saw, with DALL-E. You can connect it with StyleGAN, as some people are doing. I'm sure you can connect it to something like GPT-3, and it's going to be an exciting world. All right, that was it from me. Thanks. Bye-bye.